Here we keep talking about the smaller coupling in the lattice. And yeah, I make it a little more clear here. Before, all we talked in the last lecture is they are without considering a special symmetry of the lattice. They are symmetry independent part. Now we will focus on these symmetry related terms, but some of them actually not that actually sensitive. It's really general. Later, I hope you will get a feeling like in the lattice, this is really a general effect. And we will first start slowly with this Rashba effect, and then what is the Dresselhaus effect, and then later we go to the general term. For example, we will use graphene and other material as some example. Okay, we skip him. They are the atom-dependent part. I repeat a little. One is related with the spin orbital splitting of the bands. Then the second also related with this called the Darwin term or the sp contraction effect. They switch the band order. And this mainly happens for the valence s or p electrons. And then this is, now we start talk about the symmetry related part. And yeah, I have to see is here next, I only have 10 slides for next 2 hours. And let's really slow down. Feel free to ask questions. And yeah, to help me to fill the time. Yeah, thank you. Where is I? This one? L. Sorry, just yeah, should be L. And yeah, here let's see symmetry, like time reversal symmetry. And anyone familiar with time reversal symmetry or not familiar? Yeah, time reversal. For example, let's see spin. When we reverse the time, spin will flip. Yeah, for example, you know why? Or it's common for you? Or yeah. Yes. Yeah. Yeah. Exactly. Yeah. Spin. This we just think spin semi-classically. It has a current circling this way. If we reverse the time, this current direction will reverse. Then the spin direction reverse. And this is tell you the spin will reverse the direction. The angular momentum is same. Yeah. And this momentum will reverse. Then the spell coupling S dot L, they will not change the sign because they both reverse. And then for sure the momentum will reverse. Yeah, we can move in this direction, then it will move back. And then time reversal symmetry tell us, like if you have a band, the En is the eigen. Yeah. Which?
For speed, the same rule.
Yeah.
Time reversal symmetry.
Oh, sorry, typo. Inversion symmetry, different. Inversion is different.
No, I mean in quantum mechanics.
Yeah.
Including quantum mechanical description.
Yeah.
We have the same rule for speed.
Yes. Angular momentum. Yeah.
But we can treat it as a current in quantum mechanics.
Yeah, not. Yeah, should be similar. Yeah. And here, let's just say here, if we have a band, this is the band energy for a given spin and given momentum. When we reverse the time, then we get another band have opposite spin and opposite momentum. This simply follow from this part. If we have inversion symmetry, you do inversion means space inversion, and like from R to minus R. And here, then spin and this momentum doesn't change, but this moment will change. And then you will get a band with in the minus K another band, but with the same spin. And from here, you will get, suppose here, time reversal tell you, sorry, S and Chi. And this is time reversal symmetry. If you have inversion symmetry, should I write IS? or ISS. And will tell you, in the opposite momentum, you will have this, right? Do a little mathematics, you will exactly have something like this. This you will get S chi, minus S, same momentum. They simply tell you at the same momentum, you will have two states, one with up spin and down spin, opposite spin. And this tell you at every momentum, it's double degenerate. It's this band structure. Two spin, they overlap everywhere in the band structure if you have these two symmetry together. And this band structure looks like this. And one example is, for example, like graphene or silicon. And this material, they have inversion and time reversal symmetry. Time reversal symmetry, okay, if you think a material just means it's not magnetic, and there's no magnetic defects or impurities, and just a common material. And suppose if we don't have inversion symmetry, if we break this one, if we break this symmetry, then this relation will not hold anymore, and they are not equal. And then that means at a given momentum, spin up and down, the energy will be different. And this is the consequence. At the same momentum, spin up and down, they have different energy. And here, you get it. This is the simple band structure. The red and the blue, simply you can take it as the band structure dispersion for different spin. Is this clear? Yeah. And here, from this simple symmetry analysis, we already get like if some symmetry is lower, you easily split some degeneracy. And actually, this one, like we already see, like here, like what can we do is here. For example, here we see for a given momentum, two spin have different energy. And for a given spin, it's not symmetric between the left and the right. And this is a typical Rashba band, as we will see here. And then what is the Rashba effect? And this is usually referred to a surface system. And as I already mentioned in the last lecture here, if we have a surface, what will happen? Yeah, a surface here, this is the material inside, this is the vacuum. And here, the electron move on the surface. It will feel some attraction from these ions, these nuclears. And then on the surface, there's another electric field. This electric field happens for every surface. Like this is called, or you call it something, we know there's a kind of work function. Electron have to overcome the barrier, get out to the vacuum. Otherwise, your material, all the electron get out. And there's an electric field point outside to confine all the electrons on the surface. And that means if you have a material, its surface, you have kind of surface layer. What shall we plot the potential? If we have a periodic perfect material, there's no surface, this is your periodic potential, right? This is a potential, this is the potential. And the electron just move here, and you get a band structure, and then this is for bulk. Then if we cut here, there's no this part anymore. And what will happen in the potential? You will generate actually another electric field, E here. And to make then the consequences, the vacuum has very high potential because electron cannot go there. And then this is the one additional potential, how I plot it. Like here, this is the vacuum. Vacuum just means its energy is super high. The electron cannot go there. And then the consequences here, in this energy, okay, you can think there's a hard wall here to stop the electron go out. But that means here, there's usually form a kind of potential barrier for electrons, just confine them there. And well, here it's simple argue for electron, but if you have a semiconductor has holes, and there will be opposite potential, but they will be equivalent. And then there's confine a layer of electron here. Then this electron, let's think about this surface. That means there's just a very narrow layer of electrons on the surface form a 2D electron gas. This 2D electron gas directly comes from this potential, this surface potential here. Then it's moving in 2D. Now we have a 2D system. Like this 2D electron, they live on the top of the bulk. Below this 2D layer, there are just some positive ions. Here is vacuum, and it's moving only here. And then let's just repeat what we learned. Yeah, here we have an external electric field. When electron moving, it has a velocity. And this velocity, this motion will generate an effective magnetic field, this E cross V term. And we just repeat, this is the same in atom, right? Even in the atom, as we talked. And here we get this B term, and we can write down the spin-orbital coupling, or maybe I just copy and repeat. Let's. Whoa. Then you will see, like first, what happened? This is the electric field. The electric field along the z direction get out of the plane. And we have the magnetic field. It's related with the E cross V. V is the velocity of the electron. And then what is spin-orbital coupling? As we said, this is the moment of the spin and dot this effective B field. Then let's go ahead, just copy them, everything here. And we will get something, maybe the unit, there's something here, whatever. Yep. Oh, good question, sorry, I should say. Like the E field, the plane is up. This is the Z direction. A fixed coordinate, just fixed. Yeah, fixed. This is a normal lattice coordinate. Yeah. When we switch the coordinate, we just want to understand this B field. Yeah. Now we make it easy. We come back. We write everything in this way. And here, we get a spin-orbital coupling term. V is the velocity. E is the electric field on the surface. This is the polymetric of spin. This is just spin. And then what happened here? And it's not. Then this form, you can rewrite it in a way. Sigma cross P. P now is the momentum, dot Z. Oh, okay. Maybe let's see a little. What is E cross V? What's this direction? E is out of plane, V is go right. And then suppose electron is going to the X, go to this X direction, and this is Z direction. Then V cross E actually is the minus Y direction in plane. In plane. Like electron, this is the field. Electron moving this way, but it's the field in this direction. And then the consequence of this field is like, then the electron is just want to push the electron spin to align with the field, right? That means when it's moving, its spin always pointing this way. And but if opposite, spin is in this way. And then we will write this formula in this way. Sigma is the spin, this is the momentum, and alpha is the constant. Like related, we derived from the strength of the field and everything. We put everything in alpha. And here is the sigma cross P. P is the momentum, sigma is the spin. And here, just repeat. Sigma and dot Z, this means the in-plane projection. This simply means whatever you go, the sigma and P, they always prefer perpendicular. the momentum and the spin direction. They prefer perpendicular to each other, and they form a special chirality, but we will see it later. And important, well, there is some constant here. We put everything this into this constant. And here, important, let's see a little about the constant. What happened here? Alpha is 0. What is related? First, it's related with the strength of the electric field. That means this, yeah.
So V, when you go from V to V, you just write V equal to MV?
Yeah, you just write that, MV. That's why you get the M term here. Yeah, P just MV. That's,
And then when you
go
go to K space,
to K space.
are you going to put V is equal to HRK?
Yeah. Just as you like. Here we just assume a parabolic band. Yeah. And here we know here for sure this alpha should be proportional to E, to the strength of the field. We know this stronger field, you will get larger B field here. That's clear. And then the second is actually it's related with this square. This square actually it comes from the strength of the spinor coupling, the intrinsic atomic one. As we said here, yeah, these electrons, these out electrons, its strength of spinor coupling is proportional to this square. And here is same. This means this electron still live in the lattice. It still feel the lattice field of this nucleus and in the lattice. And it's field 2. One is the electric field. Then the second is still the electric field happening especially on the interface. That means like if this interface is super sharp, and this may make this electric field is stronger. And if we make it very smooth and maybe like very amorphous or make some interface with another material, then this potential can be solved or can be stronger. It depends how do you design it. Then let's see an example. Like here, this term, what is this term is? Or what will happen? Suppose we have a parabolic band, as I said here. This is just a free electron dispersion. And if we consider the spin, how to write its Hamiltonian, suppose this is spin up and spin down, here up and down. First, without consider any spinor coupling, they are just parabolic bands. Then you have here in this, when there's h bar is taken away, or whatever, doesn't matter much. In this sense, they're degenerate. They're just parabolic bands. And about in between, there's some coupling because, like, we remember this Rashba term is sigma cross p, or like sigma cross chi. Does the some term? Actually, what does it mean? It means like sigma x ky minus sigma y kz. Maybe a minus sign here. That's all. We know this sigma is a matrix, right? It's a just a 2 by 2 matrix. What I try to write is just put this matrix here in a new 2 by 2 way and add the diagonal term, this one. And here we get the alpha k plus, alpha k minus, and k plus and minus is kx. And yeah, just a notation for this. And we get one off diagonal term. And this term, what does it mean physically? Simply means this is the overlap between the upspin and downspin term, and this is the spin splitting term. And this exactly the rule of the spin-orbital coupling. And if you diagonalize this matrix, Is it clear from here to here? Yeah, here just polymetrics, and we put here. In this case here, there's no. What's the full Hamiltonian? Full Hamiltonian is H0 plus this Rashba term. This is the Rashba term. H0 just is this part, the kinetic energy, and we put it here, and then what we will get is actually it's a band structure in this way. Should I write? Oh, this is the result. If we fully diagonalize it, you will get the band dispersion in this way. This is the original kinetic one. This is a kind of perturbation due to. Yep. This is to tell you. At the beginning, this is a parabolic band. Later, suppose alpha is positive. Alpha is a positive value. And then, for the positive sign, you will get a band. Its energy, oh, it looks like all the positive chi is increased, but negative chi is decreased, right? And then, for this minus one, just its energy decreases a little in this way. In the end, you get two splitted bands, as shown here. And, oh yeah, I just learned. I should acknowledge this figure for you. And here, this is just another example to show you, like, if we have a really external magnetic field, we split the up and down spin of a band structure. And what we will get, we simply get a spin splitting, up spin and down spin. This is Zeeman splitting. We just get a splitting at every key point, but different from this way. And yeah, actually here, this degeneracy is related with time-rose symmetry. And we don't have to mention it too much. And you see already clearly, here actually positive minus, they corresponding to different spin. And here you have a spin this way, here you spin opposite way. Different spin this split. And this band structure actually is exactly this way. Like in a system, you don't have inversion symmetry, because here on the surface, you don't have inversion. And on this surface here, surface just naturally break the inversion. In a lattice, suppose originally you have inversion, but here you don't have it anymore in the z and minus z direction. And although we are considering a 2D system, just 2D parabolic band here, actually the 3D, the z direction is still there, it still survives. And most important is this electric field. And then here, this third dimension, the effect of this dimension here, give you the Rashba splitting. You will get such a band structure. Then, interesting is this is the Fermi surface. What is the Fermi? Fermi surface is simply like you cut, get this energy, you make a cut. And then what you will get is two rings surrounding the center of the gamma point from two bands. Actually, these two bands here, you will see the spin vortex. First, for example, here at this point, the momentum is go to x direction, and its spin is point to y direction. They always in this way. Yeah, you see, as you see, if you go around this loop, everywhere, they always perpendicular. And here, just this way is opposite. It's opposite just because here, there's a minus sign here. You just switch it, change it. And, okay, there's a little more. This is the detailed solution of the wave function of this Hamiltonian, but it doesn't tell you too much. And yeah, by the way, you can exactly suppose we know nothing about the physics here. We just have the Hamiltonian in this way. And you get this 2x2 matrix, you diagonalize it, you get the wave function. This is the wave function. Then the spin direction, you can just calculate it from the expectation value of this polymatrix. And you get is either x, y direction or y direction. And then the result is same, like this chiral, they always log together. And here people commonly call this system as like a spin orbital locking system. And locking simply means you change the momentum, spin change at the same time. They always locked in this perpendicular way because of there is a sigma cross chi term. This is for a 2D case on the surface. And here, suppose we go a little forward. We go into the bulk. We go into the bulk. Now it's a 3D system. And what can happen? And in this system here, inside the bulk, I just order these ions in this way. And this lattice, obviously, it has inversion symmetry. But suppose we put the red is another. For example, this is gallium arsenide. This is gallium. The red is arsenide. The electron will feel different charge, different electric field. When electron moving in between them. For sure, at the beginning, inside the bulk, it does not feel much difference. If you have too many positive here, if you move in this way, somehow in this region, the electric field is averaged. There's 0. But if you have a slightly positive and slightly negative one, ions, like for example, this is arsenide, this is gallium. If this is silicon, this is another silicon. And the electron move here. For sure, we have a strong electric field, right? And then there's no reason we exclude the small coupling effect here. And for sure, this electric field and this velocity, we just apply this formula, and we believe this system must have special spin-orbital coupling effect. And this was derived in the very early time, maybe it's in the 1960s or 50s, by Dresselhaus. And this term actually, like this is the Hamiltonian. I don't want to go to too much detail, but you will see this will be a very simple picture. Like here, this is the Hamiltonian. Omega, just a matrix, just think it as a matrix. Oh, yeah, it's a tensor here, dot sigma. Sigma is the Pauli matrix. Omega is a vector. And this is the Hamiltonian. And then we can solve this Hamiltonian as we did for the Rashba system, and just as we did here. We have another 2 by 2 Hamiltonian. And then we solve it, then we can get a form. Actually, it looks like in this way. Now let's remember, I remind you how the Rashba looks like. Oh, Rashba is here, luckily. This is the Rashba. Okay, read the sigma x ky here. Oh, in the back. Okay, good. Here is sigma x ky minus sigma y kx. But in the Dresselhaus time, here is sigma y ky minus sigma x ky. And, well, this just tells you they are very different. But here, as we said, this is a 3D system. This material, the electron travel in 3D. This is this Hamiltonian here, actually here, the K momentum. 3D just tell you your momentum has Ks, Ky, and Kz. And here in the Rashba here, because we think about a 2D electron gas, there's only Ks, Ky. Yeah. Sorry, can you repeat the question? Yeah. In the bulk. Just think in the bulk. Yeah, now the electron is inside the bulk. Yeah, Rashba only refers to the surface. Yeah, this is just because of history reason. Yeah, very good question. This I will see. This Hamiltonian here actually is a 3D one. Just to visualize it, well, we can project this 3D band structure to a 2D. Like there's X, Y, Z. We can look at the band structure in the Ks, Ky plane or Ky, Kz. But it's hard to see X, Y, Z and energy. It's a 4D band structure.
Because in the band company,
Simplify what?
because your B is not a periodic potential.
Yeah.
That is, so you have terms approximately
Yes, right, roughly. Sim1. Okay. This is just project to one plane. Yeah, as I will see here. This Hamiltonian only corresponding to here. Only corresponding to this picture. Like this picture tell you like just project this Hamiltonian to some plane. And this is the spin texture only for this term. In the bulk. In the bulk. Only in the bulk.
So why do you have a Rashba term in the bulk?
Or sometimes what happens, there's on the special surface, there's contribution from the bulk projection at the surface.
Surface?
Yeah. You project to one surface when you do the study.
When you say project, you mean in K space or in real space?
K space, but they're same, right? You from 3D project to the XY plane, it's the same in the case KY. Yeah. Well, this is not the most important part. But indeed, in some plane, you see, you have the same.
One is omega vector.
Which one?
The omega vector.
Omega.
Yeah, why does that structure?
I will mention it later. Just see. This is just complicated mathematics. I don't want to go to too much detail, but here I just want to remind you here. Here you see there's this chirality looks similar, really similar like Rashba. And what's this three Fermi surface from? For 3D system, its Fermi surface is a sphere, right? Then at every K point you can define a spin. And this one, you cut this sphere in the 001 plane. This one you cut along the 111 direction. That one you cut in another 110. Actually, if you look at the 3D, this is really a 3D case. Yeah, it's beta. Yeah, it's yeah. Okay, I will come back. Yeah, here actually, if you put them together, you will get a 3D Fermi surface feeling. How it looks like? Actually, it looks like just suppose this is the 111 direction. I make a rotate, and there just everywhere you cut a plane. Every plane is a Rashba plane. Looks like this one. Looks like this one. And then this just means like actually this 3D Dresselhaus term is not very different from a system you have a many layered Rashba, right? And why it happened? First, I mentioned actually this Hamiltonian is only written down for zinc blende lattice, for zinc blende material, and because this is from when people study a lot for these semiconductors like gallium arsenide inside and perpendicular to this field, it will feel the strong spin coupling. And then since Rashba, this alpha is related with the strength of the field and this z square, I would expect that this beta will have a similar scaling in the energy. Comparable.
So this beta is related to traveling perpendicular to the x-ray?
Yeah, so we think this dipole field is this direction. Then this traveling is in-plane traveling.
That's the alpha.
That's alpha and beta, they have same origin, this I try to say. Yeah.
But you won't get something similar to Rashba if you travel in a different direction.
Yeah, if you travel in different direction, like a parallel to this dipole field, you don't feel it. Yeah, because the B is E cross V. Yeah, because always about that. Yeah, whatever this happens on the surface or in the bulk, as long as there's a field, whether this field from dipole field, from electronuclear, or from the surface potential, and just the electric field. For electron, you just see an electric field, right? It has velocity, then it feels the magnetic field. And yeah, actually, for a different system, we just keep repeating this formula. And then let's see a little more. Actually, we already said is this Rashba system. It's breaking inversion symmetry, as I said, on the surface. Here it's breaking inversion in the bulk. Then that's the origin of this dipole field. is positive and negative. And here we always assume we break inversion. Then inversion breaking generates some strong electric field. Then is there a possibility like there's no such inversion symmetry breaking? Are there still strong electric field? Let's first just observe something simple, just from here, for example. If electron travel inside the bulk, within the bulk, very close to one material. Oh yeah, just let's see. It travel here. Here, in this position, is still some net electric field, right? And you cannot exclude it, at least. There should be something happen. And for example, also like, there's a positive, and there's another something. When electron just travel through, it feels something here, some electric field, also feel some field here. And whether this electron is, whether this position is not perfect symmetry. And there's always some possibility to give you such electric field. Yeah, as long as you agree, this additional electric field will generate this Spin-orbital coupling effect. And then now, let's see an example of graphene. For a long time, I think people really believe graphene can have Spin-orbital coupling effect. Yeah, actually, it's really weak. But here I mainly mention this physics, and it really matters in other materials. And here in most of the physics, the system actually, we keep repeating it's like as long as there's some local electric field, whatever this field from, and the electron pass through, then it will generate magnetic field. Magnetic field work on the spin. We keep talking about that. Now we go to graphene to see whether this can happen in graphene. Graphene, we know this honeycomb lattice. And then this is the band structure, the Dirac coin. We saw it many times. And this Hamiltonian actually is very simple. If you only assume the first nearest neighbor hopping, this Hamiltonian, just the first nearest hopping, electron hopping from one side to another side. And from this tight banding model, considering the crystal symmetry and the hopping direction, that means, then you will get a band structure like this. And many Dirac coins at the K point, the boundary of the Berlin zone. And this is the, yeah. And then this is the only, you think about first nearest neighbor hopping. And if one think a little more, what can happen? Like you include the second nearest neighbor. Let's